Be another second. All right. Thank you, everyone, for sticking around. So as Jay said, my name is Mitch Revalski. I'm a graduate student at Georgia State in downtown. And today I'm going to talk a little bit about how black holes grow. And so in addition to some time at the end for questions, I've built the talk with a couple of minutes throughout for questions. So please, at any point, if there's something that was confusing or something that you thought was just really interesting and you want to know a little bit more about it, just throw your hand up and ask. So it's a talk, but I want it to be interactive. So if there's something you want to know a little bit more about, please feel free to ask throughout. So when we look out into the universe, we see galaxies. No surprise, right? Galaxies, which are these massive bodies made up of stars and gas and dust and you and me and all that sort of stuff. And they come in a whole variety of shapes and sizes and forms. Some of them have lots of stars. Some of them only have a little bit of stars. Some are very blue. Some are very red. But most of them have one thing in common, and that's that they have a supermassive black hole at their center. And so Jay did an excellent job introducing basically 3/4 of my talk, but we'll go ahead and still talk about a few of these things. So on the left here is just an artist's picture of a supermassive black hole at the center of a galaxy. And again, we're talking about something with millions to billions of the times the mass of our sun, but it's in a very small volume. It's occupying a volume, maybe say the size of the solar system. And so around that supermassive black hole, we have this accretion disk, all this material that's swirling around the black hole, slowly working its way in. And basically it's being squished and compressed and squeezed down. And when you take material and you squeeze it, just like gas in your car engine, it heats up and it emits a bunch of energy. And in this case, that energy is just in the form of light and heat. So if we have a supermassive black hole at the center of a galaxy that's actively eating, we get an active galaxy or an active galactic nucleus. And so on the right here is an actual image, not an artist's conception, it's an actual image of an active galaxy. And so we can see we have a galaxy with these spiral arms, and they're working their way into the center of the galaxy. There's a ring of stars that are being born all at the same time. And basically all of this activity is going on around this active galactic nucleus that's hidden somewhere way down in there, much smaller than a single pixel. So we can't see it directly, but we can see everything else around it. And so one of the most important things to come out of modern astronomy is that supermassive black holes and their galaxies are tied together. We see that the size of the black hole and the size of the bulge of the galaxy or the velocity of the stars moving around it, they're correlated. Basically, one matches up with the other. And so the question is, why is that? Because the supermassive black hole has an extremely strong pull of gravity, but only once you get very close to it. And for the rest of the parts of the galaxy, it's like you having a magnet and pointing it at a paperclip a mile away. It's just not aware of that pull. Most of the galaxy is basically unaware that the black hole is there. And so the question is, why are these two things linked? And so if they're not linked now, what we think might be the case is that they were linked at some point in the past. Basically, they grew up together over time, and that way the size of the black hole is tied to the size and the properties of the galaxy. And so if we want to actually figure this out, we want to study this in detail, we have to study the black holes as they're actually growing. And so we want to look at active galaxies. And so again, Jay did a really nice job introducing this. We have material that's falling down on into this supermassive black hole in this artist's picture here, and it's releasing an immense amount of energy back into the galaxy in the form of light and heat and all of those things. And so as the material is falling in, it's pushing all this light and energy out into the galaxy, and that has to go somewhere. It has to impact the galaxy somehow. And so this is one of the ways that we think this process could happen, that the black hole and the galaxy basically co-evolve to end up at this final state. So we have this process of what we call feeding and feedback. So basically the supermassive black hole is eating material and it's consuming material, and then it's sending feedback to the galaxy in the form of light and energy. It's pumping this energy back into the galaxy. And this is what drives these powerful outflows that Jay mentioned. Basically you just have so much light and energy, it's able to push and clear out material into the galaxy. And so this might be one of the ways that the supermassive black hole basically regulates how fast it can grow. Because the more rapidly it tries to eat, the more energy it also puts out and the more material it can actually blow away. And so it might be this kind of self-regulating process. And so in order to see if this is the case, we actually need to study these in detail. And so Two of the hardest things to picture in astronomy for me are size scales and building up a mental picture of what we're talking about. So let's do the first one, which is size scales. So Jay and I both have had the same advisor. We tend to structure talks very similarly. This is just, kind of a Milky Way representative scale. And if we look at the supermassive black hole and the extent of that narrow line region, these slower velocity clouds, the supermassive black hole and the accretion disk and all of that is basically contained within a single pixel in this image. It's actually much smaller than that single pixel. And yet this single pixel is basically affecting a large chunk of the galaxy. And these outflows can extend out into the galaxy, but the rest of the galaxy can also be basically heated and warmed up and extend out to a very large portion of the galaxy. So we have this very small volume that is impacting a large portion of the galaxy. And so, okay, now we know what we're studying and kind of what we're looking for. Yes? Yes, so ENLR is just extended narrow line region. So basically, it's regions where all this gas is not necessarily being blown out. It's kind of just being heated up and disturbed a little bit. Any other questions? Good. Okay. So, what are the goals? The goals of my thesis project are basically to characterize these outflows. How powerful are they? How far do they extend out into the galaxy? And essentially, what are they doing? Are they impacting the interstellar medium and causing stars to form? Or are they impacting gas clouds that are trying to form stars and tearing them apart? Are they moving elements around throughout the galaxy, basically stirring things up? These are the kind of questions that we want to answer. And so these are the only two equations in my whole presentation. And so basically, the two things we want to know, first is the mass outflow rate, and that's literally just if you're standing at some point with your clipboard and you watch the amount of gas going by and you tally it up at the end of the year, how much stuff flew by you. Basically just how many solar masses or kilograms, pounds, whatever you like, how much material went by you in the course of that year. And that we can compare to how much the black hole is eating and see if it's more or less. The other piece is just normal kinetic energy. It's 1/2 mv squared. Basically, how much energy is being carried by this outflow? Is it just a little bit? Are we not really impacting the galaxy, or are we using a sizable portion of that energy that's being put out by the AGN? So, of course, we're going to need a sample. We need galaxies to look at. And so if we look really, really close to us, basically we don't find many active galaxies. And if we look very, very far away, then as Jay mentioned, these are basically point sources, these very bright quasars. And so we can't actually see these outflows. We can't actually map them out. And so if we look kind of in the middle where things are just right, we get these active galaxies that have outflows, and we can actually see them on the sky. We can actually see them as a resolved structure, just like when you look at the moon and it's a resolved structure on the sky, as opposed to a point source like a star, which is unresolved. And so what we do is go out and look for some of these galaxies. Here are a few of the ones I'm working on. And basically, they're just arranged by distance. And so the ones that are closer tend to be much bigger on the sky. You can see some of them have beautiful spiral arms and structure like that. And then as you go further and further away, they basically get smaller and smaller because they're further away, but they also tend to have bigger, more powerful outflows. And so today, I'm going to focus on one in particular, which is known as Markarian 5783. That's just its name in a catalog. And so in the background here is this giant Sloan image. And unfortunately on the bright part of the screen there, that's the galaxy we're going to be looking at. So just to show that in the context of the sky, it just looks like any other galaxy. So we'll go ahead and we'll zoom in on that. And we can zoom in and we can zoom in to our heart's content. But at the end of the day, from the ground, we can only get so much detail. Basically, the atmosphere gets in the way and it blurs our imaging, and so we can't see things as well as we could otherwise. So what we really need to do is we need to go to space and use the power of space telescopes like the Hubble Space Telescope. So there the atmosphere is not in our way. We can see things in much finer detail. And we can also put a number of filters into our telescope. And basically what those will do is cut out all the light that we're not interested in, and we can look at just very specific pieces of light. And so in this case, what we tend to look at is light that's coming from excited oxygen. So an oxygen atom where the electrons are jumping up and down, and they're emitting light. And so when we do that, we get something that looks like this. And now we can see there's way more structure in there. There's a lot more going on than we could tell from the ground. We needed the space-based data to do this. And so we can go ahead and manipulate this image and kind of pull out some more of the detail. And when we do that, we get something that looks like this. And so this is what I like because it's an actual picture of what we're studying, these outflows. And so down in the very center, hidden down there somewhere in that little bright point, is this supermassive black hole that's pumping out all this energy. And then we can see these dark, dusty lanes of material that's within the galaxy. And then we have these ionized arcs of narrow line region gas, basically this hot, excited gas that's emitting light that we can use basically as a tracer. And so the question is, what of this material is actually part of the outflow? How much of this material is being blown out? How much of it is just rotating along in the galaxy as if nothing's going on? That's what we want to understand. And so to do that, we'll need some data. And so again, as Jay mentioned, a lot of our data comes from, first, the Hubble Space Telescope. So the data for my thesis actually was taken almost 15 years ago for a different project, and now we're basically repurposing it to do it for this project. And so again, as Jay mentioned, that's one of the great things about a lot of these space missions is all the data is free and out there and public to play with. You can go to the archive, you can download the same data I'm using on my thesis and use it for an entirely different project. The other piece comes from the Apache Point Observatory, which is in Sunspot, New Mexico. And actually you can see in the very background here, this is the Sloan telescope, which is where a lot of the data that Jay and his students have been working with. And then here is the 3.5 meter telescope, and this is a person here for scale. So it's actually quite massive, and it's a little terrifying to ride around on the gangway there, but it is fun. So this is where our data comes from. Here are just a few more pictures that I took when I was there visiting and being trained on the instrument. Here I am after having not slept for about 28 hours and still somehow smiling. I think I was half asleep just walking around sleeping. And some of the actual instruments that are bolted to the side of the telescope. So some of the things that we have access here at GSU. So we can gather, with these telescopes, we can gather images, but one of the biggest things we gather is spectra. And so I like to think of that as the astronomer's Rosetta Stone. Basically, spectra tell us everything that we could hopefully want to know about an object. And so what we do is we take our galaxy and we block out the portions of it. We look at just a little piece of it, and we take that light, and just like shining a flashlight through a prism where you get a rainbow, we take that light and we spread it out by its colors in order to see what's there. And so if we take this light from this narrow slit and we spread it out, we can see that there's multiple images of different colors that when you add them together, you get what you see. And so in this case, this is light coming from hydrogen and nitrogen, and there's a whole mess load of others, but basically we can see where there's light in the galaxy, we get light in our spectrum, and so we can use that to analyze what's going on. So here's some big pictures, but you end up with something like this, which is the reverse of what Jade showed. So this is an emission spectrum. So basically we have blue here on the left moving red to the right, and then how bright the light is. So we have all the different colors of light coming just from the stars and the gas and the dust, and then we have these very specific emission features from this excited gas. So just like you look at a neon sign and it glows blue or orange or whatever color they've set up, these emission lines are that same type of process. We're exciting that atom, and it's emitting a very specific color as those electrons jump up and down very specific energy levels. And so there's a whole bunch of different lines here that come from all sorts of different types of gas, and we use this in order to basically paint the full picture of what we're trying to look at. So you might recall the two things that we needed were the velocity and we need the mass. So the velocity just comes from the Doppler shift, which Jay covered, and basically what we can see is we have the center of the galaxy in the middle and then moving outward, and basically this black line is a very rough approximation of what you might expect for a galaxy that's just rotating around nice and gently. And you can see there's this interesting sawtooth pattern which doesn't fit that at all. And so that's what we determine is the outflow. Basically material is being ejected and blown away from the supermassive black hole and then slowing down and then just turning into normal rotation at larger distances. So basically this is how we get the first piece of what we need, is we use the spectra and the Doppler shift, we get the velocity. In the context of the actual picture of the galaxy, what this means is this inner region here, basically all this stuff in the inside, that's what's being blown out away from the supermassive black hole, and the rest of the material out here at larger distances is just continuing to rotate around. So this black hole is powerful enough to push some of the gas out, but then at larger distances it just doesn't have enough energy, it just doesn't have enough juice to keep pushing the material out, and so it just keeps rotating along nice and clean with the galaxy. The other part that we need is mass, which involves quite a bit of modeling. I'm going to sweep a lot of the details under the rug, and if you'd like to know more, you're more than welcome to ask me later. So the point is we have this spectrum, and we have it at each point along the galaxy, and basically with any type of modeling process, we want to make a model, and we want to compare it to our observations, and we want to see if they match. And if they match, great. That almost never happens. You make a model, it is horribly wrong, and you fix it, and it gets a little better, and you fix it, and it gets a little better, and you fix it, and it gets a little better, and eventually you hopefully converge on an answer that actually makes sense. Basically, can we match all these different emission lines? Can we match the shape of the spectrum? And then from that, we can say, okay, there's this amount of mass here, this actual physical amount of stuff, that if I was to go there and measure, I would measure that amount of material. And so to do this, basically we have codes, and what you need to give the code is basically what you see. So you need to tell it how bright this AGN is, how much light it's pumping out. You need to tell it how much of each gas is there, if there's any dust, how far away it is, those types of things. And then basically what you get out is a model spectrum. So you get out a model spectrum, and you compare it to your observed one, and you see if they match. So lots of details. Insert all the details here. Insert 3 years of laborious PhD work into that one bullet point. It's not soul crushing. And then you compare the models to observations and see what you get. And so without further ado, the results. So circling back, you might recall the two things we were interested in were the mass outflow rate and the kinetic luminosity. Basically, how much material is being blown out and how much energy is being carried with it. And so the important thing is this has only been done in great detail for essentially one other galaxy. And so for the first one that I'm working on now, this is the second one, and I will be doing more for my thesis. And so what we get is something that looks like this. So here we just have distance from the center of the galaxy. Just had lunch. And basically, if you just multiply this by 3, you get light years. So basically, we're looking out to about 2,000 light years into the galaxy. And this here is the mass in hundreds of thousands of solar masses. So basically, as we move out into the galaxy, we're getting more and more mass, up to about 300,000 solar masses. And if we total all this material up, we can figure out how much is actually being blown away from the black hole. And that turns out to be about 2 million solar masses in this case. So it's a lot of material that's being affected by this very, very tiny AGN down in the center. If we go ahead and actually look at those mass outflow rates, so just stand there with your clipboard, the amount of material that's flowing by you. At its highest, basically 3 solar masses worth of gas would move by you, which doesn't sound necessarily like a whole lot when you consider that galaxies have billions of stars and hundreds of millions of stars, but if you add that up over a long period of time, it ends up being a lot of material. And so in the gray dots here is basically the other galaxy that this has been done for, and it has a black hole which is eating much more slowly. And so it's not nearly as powerful, and it can't drive as much material to as large of distances. So this is important. It makes sense that if the black hole is pushing out more energy, it should have more powerful outflows, and so far so good. That's what we're seeing. The world's foremost expert, it would either be our advisor, Mike Crenshaw, or Brad Peterson, his advisor. No, this work isn't foot in mouth. No. So it's showing that as we go to more powerful galaxies, we get more powerful outflows. And so we're actually going to try to extend this the other way, too. We're going to try and look for the absolute tiniest, least powerful, wimpiest AGN you can find and see if they have basically little tiny outflows or if they're just not powerful enough at all. So, well played. Well played. The other piece of this is the energy. The numbers aren't particularly important. Again, just the point that as you move out into the galaxy, the material is being driven faster and faster, and then it starts to slow down and move slower and slower, and you get less energy. And so we can compare this to the total amount of energy that the AGN is putting out, and basically if it meets certain models, we can say, okay, this AGN is effective. Basically, it's going to be able to clear out this material, which has a lot of consequences for how much the black hole grows and how stars form, all that sort of stuff. So with that, I'll wrap up. Point being, we think that galaxies and their supermassive black holes must grow up and co-evolve together at some point in order for them, basically their sizes and masses to be correlated. And one way that this might be is by studying these mass outflows. And the only way that we're really going to know is by quantifying them in detail, which requires good observations and lots of time-consuming PhD modeling. So with that, I'd be happy to take any questions. So the data that comes from Hubble was archival, and so that was taken about 15 years ago. And then the data that I took at the Apache Point Observatory, that we've slowly been building up, but usually you can look at basically an object per night or 2 galaxies per night. So you have to stare at it for quite a while in order to gather a lot of light. So for that particular one, basically we looked at it for about 2 hours. And then fixing the data and processing it is a much lengthier process, but yeah. They can. So in these beautiful galaxies that have these big long bars with nice spiral arms attached to them, some people think that basically the bar might be a funnel, a way to get material down to the black hole more efficiently. And so there's some evidence for that, but the jury is out, I think, is the